So I'm going to keep talking about limits. In this video, I'm going to prove, roughly speaking, that limits are unique. So what do I mean by that? I mean that, say we have a certain limit. The limit is x goes to a of f of x, and that's L. And then the same limit is also equal to m, then L and m are the same number. So that might seem obvious, but we have to really think about the definition of it. Like, what does it mean for this to equal L and for this to equal M? And we're going to have to talk about epsilons and deltas to do that. So let me first give away maybe an idea for the proof. Say we have a number line. If L and M were different numbers, and maybe I'm already giving away, this is going to be a proof by contradiction. We're going to suppose that L and M are different numbers, so they're on different places of the number line. What we can do is, when we write this limit, I'm not going to write the whole definition, but there's part of it that's saying that f of x minus L absolute value is less than epsilon. When I write this one, it would be m instead of L. What this means is that f of x is within a distance of epsilon of L. So like, if this is like L plus epsilon and this is L minus epsilon, then this is saying that f of x is in here. And this would be saying that f of x is in here. Like if this is m minus epsilon and m plus epsilon. And I'll be able to get a contradiction if epsilon is small enough, because how can f of x be in here and in here if these don't overlap? So if I make epsilon small enough, these two intervals will not overlap, and then it's impossible for f of x to be in here and in here. How small does epsilon need to be? Well, in order for this and this to meet in the middle, it would be the average of L and M. In other words, in other words, it's like half of the distance from L to M. And in this picture, obviously, I'm assuming that M is greater than L. Okay. But this was all just kind of discussion and scratch work for the real proof. So how's this proof going to go? Again, like I said, it's going to be contradiction. Assume for contradiction that L and M are not equal. And now, okay, in my discussion, like I was saying, I sort of assumed that M is greater than L. Well, what if it's the other way around? What if L is greater than M? I can just say without loss of generality here. Without loss of generality, we have two numbers, L and M. One of them has to be bigger than the other one. We can just call the bigger one M. So I can assume that M is greater than L. If L was greater than M, then I would just switch the names. I would say this number that we were calling M, we will now call L, and the number that we were calling L, we will now call M. So these two numbers are arbitrary. I can assume that M is the bigger one. And yeah, so we said what epsilon was going to be. So by the definition of a limit, we can say there exists a delta greater than 0. And yeah, and by the way, I should check. That period is no longer there. Epsilon is greater than 0 as well, because M is greater than L, so the numerator is positive. So there exists a delta greater than 0 such that this implies this. And there exists some delta, and it might not be the same delta, so maybe I'll call this delta prime, such that this implies the same thing, but M instead of L. And I am using the same epsilon here. It's just this same epsilon. It's just that the deltas might not be the same. But the fact that the deltas might not be the same hardly matters. Because I can just take the smaller of the two. If I just do the min of these two, then I get both statements. So this means that absolute value of x minus a is smaller than delta. It's also smaller than delta prime. So then this is true and this is true. So I have this, and instead of epsilon, let me write what epsilon is. Actually, no, I changed my mind. I'm not going to do that just yet. So what does this mean? I can solve this the same way I normally do, and maybe, yeah, eventually... No, I'll show the work. So you take the absolute values off and put it in between epsilon and negative epsilon, and then I add L to everything, so L minus epsilon less than f of x less than L plus epsilon, which, by the way, that's exactly what I set up here, that f of x is between L minus epsilon and L plus epsilon. That's the same thing that we just got. And maybe I won't really show the work on this one. This is the same except M instead of L. So this is M minus epsilon f of x, M plus epsilon. And I'm running out of space here, but I'm almost done, so let me try to be ambitious with the space I have left. Now, what was the contradiction supposed to be? The contradiction is supposed to be that f of x is in this interval and that it's also in this interval, but the two intervals don't overlap. They don't share anything. So let's just show that the biggest f of x could be in this interval is still too small to be in this interval. And this is where I have to actually plug in epsilon. So f of x is less than L plus epsilon, and if I put that in, That's m minus L over 2. And if I get a common denominator, I get m plus L over 2. And f of x is also greater than, if I look at this, m minus epsilon. So I write that. And if I get like this would be 2m over 2, and I'm subtracting this, so I get m plus L over 2. But look, f of x is smaller than m plus L over 2, but f of x is also bigger than m plus L over 2. So formally, that's the statement that these two intervals don't overlap. So this is our contradiction. F of x can't be smaller than this number and also bigger than the same number. That's a contradiction. That's the end of the proof. Okay.